Good morning, student. We already discussed Bohr's atomic model and what are the postulates of Rutherford atomic model and radius of the Bohr's atomic model and velocity or speed of an electron while revolving around the nucleus in case of Bohr's atomic model, and we already discussed the energy or total energy consists electron in nth Bohr's orbit. Clear? Now we have to find here the spectral line or the spectral analysis of hydrogen atom. So what is spectral analysis of hydrogen atom? Actually the limitation of Rutherford model, he could not explain the spectral line of hydrogen atom, but the Bohr's modified the Rutherford atomic model and he explained about the spectral line of hydrogen atom and the spectral line which is discontinuous spectral line of hydrogen atom. Clear? So what is spectral line? Suppose we already know there is a surface or interface separating by two medium. This is suppose another medium whose refractive index mu, and here this is air medium, and when a ray of light which incident on the metal surface, suppose this is incident ray which coming in air medium. Now we have to draw a normal at the point of intersection which is 90 degree, but here we have to pass a white light and it consists 7 color. Actually it consists infinite number of color, but the visible color of light or visible color of wavelength of light which is 7, and this is angle of incident. Then while light coming from rarer to denser medium, this is the actual path or line of action or original path, this direction. Then the light split into different color. These are the different color of light in this way. Clear? And we get 7 color of light or we get 7 wavelength. If you draw a screen here, suppose there is a screen, then this angle is angle of refraction R and this angle is also angle of refraction, but this ray is known as red and this is violet. Clear? So we get all the wavelength V I B G Y O R. So we get 7 color, that is V I B, or I am writing here V I B G Y O R. Clear? And this region is known as visual region and its angstrom, its frequency wavelength 3600 angstrom to it vary 7600 angstrom. This is visible region. Clear? And we get all the wavelength, red wavelength, orange wavelength, yellow, green, bright, indigo, violet. This region is known as continuous spectrum. Continuous spectrum of light. Clear? It consists 7 color. So if here this light is white light, but we have to use here a gas, atomic gas. Suppose there is a container and it consists atomic gas like this. These are atomic gas. I am writing atomic gas. Now we have to heat this vessel. Clear? If you want to heat this vessel, so we have to provide some amount of energy to heat it off the atomic gas. So we have to use here electric current or electrical energy to heat it up. When you supply heat to the atomic gas, then radiation takes place from the atomic gas. This is radiation of light. Radiation takes place, and this radiation now pass through a prism. Suppose there is a prism, and we already know if there is a prism and if white light pass through the prism, this is white light, then 7 number of color we get here, that is V I B G Y O R. This is known as continuous spectrum in case of prism. But here this light is not white light, it is radiation after heating the atomic gas by electric current. Clear? and this pass through the this is prism, and again it splitted in different color like this. Clear? If there is a screen, then we get the particular, we get here a specific wavelength of light. Specific, particular wavelength of light, not continuous, according to Bohr's theory or according to Bohr's atomic model. While white light we use to reflect, or white light to use pass through a prism, then we get continuous spectrum of light, then we get continuous wavelength which ranging from 3600 angstrom to 7600 angstrom. But while we passing the radiation or atomic gas after heating, then we get a discrete, not continuous spectrum of light. We get here a specific wavelength of light. Specific means, suppose we get violet here, then we get blue here, then we get suppose yellow here, then we get red here. Then Vi, where is indigo? Indigo light, Vibgor G, here green, orange, and these are absent in this case. Clear? So in this case we cannot find the total number of wavelength of light. We cannot find the continuous spectrum of light which was told or which was Bohr's experiment, and due to this experiment he got Nobel Prize. Clear? So we get some specific wavelength. Clear? Suppose here wavelength is 7600 angstrom, then we get another, we cannot find here indigo, we cannot find the wavelength of green, we cannot find the wavelength of orange. These are absent in this case. So this spectrum is discontinuous spectrum. Clear? So we will discuss here about discontinuous spectra, or that is known as spectral analysis of hydrogen atom. Clear? Okay. And we already know, suppose this is the central part of the atom, this is the nucleus, and around the nucleus there is a number of orbit, and about which the electrons are revolving like this. These are the orbit of hydrogen spectrum. Clear? And this is known as fast orbit. Here n equal to 1, here n equal to 2, 3, 4, so on. N equal to 1 here, n equal to 2, n equal to 3, n equal to 4. We already know in ground state the energy, it is minus 13.6 electron volt. Always in electron volt the energy measure, and this energy, that is 3.4 electron volt, and in third Bohr's orbit this energy minus 1.51, and the fourth Bohr's orbit, that is 0.85. All the units or all the energy are measured in terms of electron volt. Clear? These are we already discussed. Now the energy of hydrogen atom in nth Bohr's orbit we can write here, that is En equal to minus 2 pi square beta square e to the power 4m and there is z divided by n square h square. Clear? For hydrogen atom you can write z equal to 1. Okay, we can write it in letter. So En means total energy in hydrogen atom for nth orbit. Clear? Okay. Now we have to heat. This is atomic gas. Now we have to heat the atomic gas by using electric current. Now while we heated off the atomic gas, the electrons are absorb energy from the electric current. When electron absorbs some amount of energy, particular amount of energy, then electrons are jump from ground state to excited state. Clear? Suppose this is ground state and here energy, that is minus 13.6, and when electron gets some particular amount of energy, then they get excited and jump to higher state. Then how much amount of energy electron gets, so that a electron can jump from ground state to, this is known as first excited state or second orbit, because here energy, that is minus 3.4. But we already know from Bohr's atomic model, when electron jumps from a higher energy level or lower energy level to higher energy level, low to high energy level, then it require energy E equal to E2 minus E1, and here E2 means second orbit. This is second orbit minus 3.4 electron volt minus minus plus, and 13.6 electron volt, which is equal to 10.2 electron volt. If electron absorb 10.2 electron volt from the electricity, then it get excited and jumps to the higher energy orbit, whose energy is 3.4. It is possible if electron absorb maximum amount of energy, which is, suppose this is maximum means minus 1.51, then it can jump through second excited state, it can jump to third excited state, and so on. But while electron jump from ground state to excited state, in excited state electron feel unstable due to instability condition, then electron now try to jump higher energy orbit to lower energy orbit. How can electron jump from higher energy orbit to lower energy orbit? There is one condition. Which condition? If electron possess now minus 3.4 electron volt energy, if electron radiate how much energy? If electron radiate 10.2 electron volt, then electron come back to the ground state again. Then this amount of energy is radiate, that is known as radiation process, and in radiation process we can say that the electron release one photon particle, photon, and we already know the photon E equal to h nu, and that is here 10.2 electron volt. Suppose there is a electron in second excited state, and this electron try to jump second excited state to ground state, then this electron release maximum amount of energy which can reach the ground state. In this way, the electron jumps to higher state to lower state, or higher energy state to lower energy state. Clear? So there is a relation I am writing here. So when electrons jumps from higher energy level to lower energy level, according to Bohr's atomic theory, we can write E2 or En2 minus En1, which is equal to a photon energy E. Clear? And here E, this is energy of nth Bohr orbit. And what is E? E means photon energy. I can write here, we can. It is h nu, which is equal to En2, or E2 means second excited state. So you can write here En2 means, this is second orbit, this is first orbit. Clear? Okay, so I am writing here En2 means here minus 2 pi square beta square e to the power 4 m z divided by n square, means here n2 square h square minus of minus and plus it is here. So 2 pi square beta square e to the power 4 m z divided by n1 square into h square. Clear? And this h nu can be write in terms of wavelength, because we will find here the spectrum of light in terms of wavelength. So hc by lambda, this is another one form of energy, and here all the quantity are constant, so we can take here this is minus n2. If we take the relation here, minus 2 pi square, here beta square e to the power 4 mz divided by here h square, then the remaining term, that is minus, sorry, here I am writing minus, so 1 by 2 n2 square plus, if you take common quantity here, then 1 by 2 n1 square. Clear? And hc by lambda, hc by lambda, which is equal to, already we know this value, that is minus 13.6 electron volt. If we use all the value, mass of electron, beta, pi, and here h means Planck constant, then you will get the relation minus 13.6 electron volt into z square. Clear? Into here, sorry, this term is z square, not z, z square, and here z square, this is z square, and z square is here. Z square divided by here energy, that is n square. This is general formula. Clear? If you solve this relation, then you will get the final relation like this here. Clear? So now I am writing here 1 by lambda, which is this term, or for hydrogen atom I am writing directly here. For hydrogen atom z equal to 1. For hydrogen like atom or hydrogen atom, here z equal to 1. So 1 by lambda can be write here, hc is numerator part. If you take next side, then it will be denominator divide. So 2 pi square, here beta square e to the power 4, here m and z square equal to 1 divided by hc here. Clear? And hc into 1 by n1 square, I can write here 1 by n1 square minus 1 by n2 square. Clear? So this is the general relation for calculation of wavelength of the light or wavelength of spectra. Or we can write another term here, 1 by lambda, which is equal to this term. If we use all the value, this is constant quantity, and this constant quantity can be write in terms of r. R into, that is 1 by n1 square minus 1 by n2 square. Clear? And what is r? And the value of r is here, this value r equal to 2 pi square beta square e to the power 4m divided by hc, and its value are nearly equal to, that is 1.09 into 10 to the power 7, and its unit. So this is constant quantity, number of orbit, or a principal quantum number or integer you can say. So this is constant quantity numerical value, and here r, and r equal to 1 by lambda, and lambda is your wavelength and its unit meter. So r can be write here meter inverse, so m minus 1, and this constant is known as Rydberg constant. Rydberg constant. Clear? This is the general expression, or you can remember one relation here, 1 by r, 1 by Rydberg constant you can write nearly equal to, that is 12912 angstrom, nearly equal to. Clear? You can remember this relation to while calculation of numerical problem, it will help you. Clear? So 1 by lambda equal to r, 1 by n1 minus 1 by n2 square, sorry, here hc by lambda, which is here this much, and by h square. But here just mistake by me, hc if you multiply here, then chq, then here chq, because ch and h square is here, so chqc, and this term also chq. This is known as Rydberg constant. Clear? So when this radiation pass through the prism, we get different wavelength of light, and this is known as spectral. And you have to remember this relation here, spectral line. So first spectral line, when electron jumps from higher energy orbit to lower energy orbit, it radiates some amount of energy, particular amount of energy to come to the ground state. Clear? So now we have to find here number of spectral line emitted by the radiation through a prism. Now let's start energy spectrum here. So we have relation, that is 1 by lambda equal to R, Rydberg constant, and 1 by n1 square minus 1 by n2 square. This is general formula. Clear? So first series of hydrogen spectrum which was given by Lymon, it is known as Lymon series. Lymon series of hydrogen atom. So in this case, first we have to draw a energy level diagram here, and you already know, suppose this is n equal to 1, and here the n equal to 2, and this energy gap, it is n equal to 3, and here the n equal to 4, 1 2 3 4, and here energy, and this energy minus 13.6 electron volt. This is known as ground state energy. Ground state energy of hydrogen atom according to Bohr's atomic model. When n equal to 2, we already know the relation, that is minus 3.4 electron volt, and this is known as fast excited state. Fast excited state energy or second orbit. This is first orbit, second orbit. When n equal to 3, then we get here, that is minus 1.51 electron volt. This is known as second excited state. Second excited state when n equal to 4, and this energy 0.85 electron volt, and this is known as third excited state. Clear? And again, if you come to the next level, then this gap is very close to the, then this gap, energy gap is very close, and the energy level now overlap each other like this. Clear? So these are the energy level like this here. Now when you will come to the n number of orbit, when n equal to infinite, at that time, because here general relation, that is En equal to minus 13.6 electron volt by n square, which is equal to minus 13.6 electron volt divided by n is your infinite square. So I get the energy, that is 0. So at infinite orbit, the energy which is equal to 0, and this energy is maximum, because here a negative sign, this energy is minimum in ground state. So maximum electron are try to remain in ground state. Why? Because here the potential energy or the energy possessed by the hydrogen atom which is minimum here. So every atom, so every electron try to jump from higher orbit to lower orbit, because here the negative potential energy, here negative energy, that is minus 13.6 electron volt, and here they experience a no force, or they experience a net force which is equal to 0. Clear? So now let's start Lymon series, and this series indicate that when electrons are jumps from higher energy orbit, that is n2 equal to higher energy orbit or higher energy orbit according to principal quantum number n2. This is higher energy, and which is equal to 2, 3, 4, 5, so on, except one higher energy orbit to lower energy orbit. Lower energy orbit, here n1 equal to 1. At that time the electron release some amount of energy, and that energy equal to h, E equal to h nu. But we have to find here the frequency, or we have to find here the wavelength in terms of energy here. So I am writing here, when electron jump from higher energy n2 to lower energy orbit, that is n1. That means when electron jumps from higher, this is higher n2 to n1, or you can choose n2 equal to 3. If 3 is here, then 3 to ground state, and 4 to ground state, and infinite to ground state. This spectrum is known as Lymon series. Lymon series. Clear? So in this case, if we want to find wavelength of spectral line, 1 by lambda r, which is equal to 1 by n1 square minus 1 by n2 square equal to r into 1 by n1. N1 is your 1, because this is for all the electrons are jumped to ground state. Step number 1 is here, minus 1 by n2. We can take 2, 3, 4, 5, 6, just the last infinite. If we use here 2, then we will get 2 to the 4. Clear? So 1 by lambda, which is equal to r, then 1 that is 4. 4 minus 1, which is equal to 3. 3 by 4, or lambda can be right here, that is 4 by 3 into 1 by r. We already discussed the relation, that is 1 by r, its value nearly equal to 912 angstrom, or 911 angstrom you can say. If we use this value here, then 4 by 3 into 1 by r, and 1 by r equal to 912 angstrom. Clear? So 3 3 is 9, 3 0, 3 4 is 12. Then we will get 4 4 is 16, 1, then 4 0 1, then 3 4 3 is 12. So we get the angstrom. This is wavelength lambda. This is fast line of Lymon series, means when electrons are jumps from fast excited state to ground state, or second orbit to fast orbit, at that time we get the spectrum or light of wavelength, which is equal to 1216 angstrom, you can say here. Suppose you can take another one example, when electron jump n2, and I am taking here 3, this is 3, and to n1, because n1 is here 1. Now in this case we can calculate 1 by lambda equal to r into here 1 by 1 minus 1 by 9, which is equal to, that is 9 1 9 minus 1 8. So r 8 by 9. Then we can write here lambda equal to 9 by 8 r, or we can write here 1 by r, its value 912. This is approximate value, so we can write here 9 by 8 into r, means here 1 by value you can write here 912 angstrom. Now cancel this term, 4 2 is 8, 4 2 is 8 11, then 4 2 is 8 3 32, then 4 8 is 32. Clear? Then 2 you can cancel it, 2, so 11, that is 4. Now multiply 9, then we will get 9 4 is 36, then 9 1 is 9 3 12, 1 9 1 is 9 equal to 10. Clear? So we get here lambda. This is first line, this is for second line. You can write here lambda 1, you can write lambda 1 lambda 2, or here lambda equal to, you get 1026 angstrom. Clear? These two relation. You can take another one relation here. Suppose there is a electron which jumps from infinite number of orbit. So you can write here n2 equal to infinite to n1. Infinite to n1 equal to 1. At that time 1 by lambda equal to r into 1 minus 1 by infinite square, and 1 by infinite is equal to 0, and here 1 by lambda equal to r, or you can write lambda equal to 1 by r, which is equal to 912, nearly equal to 912 angstrom. So here lambda we get, that is 912 angstrom. This is approximate value this case. So from these two examples we conclude that when electron jumps from nearer orbit to ground state, at that time we get larger wavelength, but when electron jumps from infinite to ground state, then we get minimum number of wavelength. So here we conclude that we can write here, for large or larger wavelength lambda, then the transition or electron jumps from the transition of an electron from higher to lower. Clear? Okay. Next thing, for larger lambda, transition of electron from nearer to ground state. For smaller wavelength lambda, then electron transition of electron, that is transition of electron from infinite to, that is ground state. Clear? These are the concept of Lymon series. And how can we find maximum wavelength or maximum spectral line, or wavelength which is maximum, or wavelength when we get minimum? This is all about for Lymon series. Clear? And here we get the wavelength, this wavelength, like here we get first case, we get a lambda equal to that is how much, 1 to, I forgot about lambda, so I am writing here lambda, that is 2 6. Suppose 1 to 2 6. Suppose this lambda, while electron jump from n2 to n1 equal to 1, and third case n3 to n1 equal to 1, at that time n equal to 1026, I think this value. And when infinite, n3 which is infinite to n1 equal to 1, at that time we get lambda equal to 912 angstrom. I am confused about this relation, I am just written here, but you can write this relation here. So this wavelength is maximum as compared to minimum, and this is minimum, but we have a spectral line here. Clear? We discussed in optics our first class, and here spectral line, first here microwave, then radio wave, and then infrared region, and this region is known as visible region. And visible region we will find here 7 color of light, VIBGYOR, VIBGOR, and it consists wavelength which is equal to 7600 angstrom to here 3600 angstrom, in this range. And after that you will get ultraviolet radiation and like that, X-ray, gamma ray, and so on. Okay, but this wavelength, while electron jumps from higher energy orbit to ground state, then this wavelength is lies, because when you come to this line, this direction, then wavelength decrease, here lambda decrease, but frequency increase. Clear? And this region 1226 or 1026 or 9126, which lies in this region. Clear? So in the Lymon series, the emission takes place in ultraviolet region. Clear? So this transition takes place in ultraviolet region, means this region which is not visible to us. Why? Because we can see, or it is visible to our eye in between visible region and its frequency 3600 angstrom to 7600 angstrom. Clear? Now let's start second a spectral line. It is known as Balmer series. So in this case, the transition of electron from higher energy orbit to N2 means higher, and this higher energy orbit, that is 3, 4, 5, 6 and so on, higher energy orbit to lower energy orbit. This is higher. When transition of electron from higher energy orbit to lower energy orbit corresponding to N1 equal to 1 means when electron jumps from higher energy orbit means N3 to lower energy orbit, this is N equal to 2. Then this is higher 3, 4, 5, 6, 3, 2, 2, 4, 2, 2, 5, 2, 2, 6, 2, 2 and infinite to 2. And this series is known as Balmer series. Clear? So in this case, we can write here 1 by lambda which is equal to R, 1 by N1 square minus 1 by N2 square. Clear? And you can use all the value and you can solve. Suppose I am solving here 1 by lambda equal to here R into N1, N1 is here 2, so you can write 1 by 4 minus here N2 equal to 3, so 1 by 9. Then if you solve this relation you will get that is R equal to 9 4 that 36 minus 9 minus 4 1 by lambda, or 1 by lambda which is equal to R, and this is known as 9 minus 3 which is equal to 5 by 36. And here lambda equal to 1 by R into 36 by 5. Clear? If you solve this relation, here lambda you will get there is a spectrum, and this spectrum is known as visible. This is visible region of electromagnetic spectrum. This is known as electromagnetic spectrum, and this region is visible to us, and its frequency 36 angstrom to here 7600 angstrom. This region, clear? And this region is for it is Balmer series. If you solve this relation, then you will get a frequency or wavelength which is lies in between 7600 angstrom to 3600 angstrom. This is visible to us, this spectrum. Clear? So this spectrum is known as visible region. We can write here when electron jumps from higher energy orbit to second orbit, then the transmission or the energy level is known as visible region. The transmission or the wavelength of light, the wavelength of transmission of electron, the wavelength of light or wavelength of transition of an electron which lies in visible region means this region is known as Balmer series. First, here this series is known as, this region is known as for Lymon series. This is for Balmer series. Clear? Next series, Paschen series. Third series, Paschen series, and here the electron transition from higher energy orbit N2 corresponding to 4, 5, 6 and so on to lower energy orbit, and here lower energy orbit N1 equal to 3 means third orbit. So from this energy level diagram, electron jumps from 4 to 3, 5 to 3, 6 to 3 and infinite to 3, and this region is known as Paschen series. So in this case we can write here that is 1 by lambda which is equal to R into 1 by N1 square. N1 is here 3, so 1 by N1 square means 3 square minus 1 by N2. You can use 4, 5, 6, 7 up to infinite. So I am writing here 4, that is 4 square. Clear? If you solve this relation, If you solve this wavelength, then this wavelength lambda, which is lies in terms of, and this lambda in terms of angstrom, and this angstrom which lies in the region. This region is visible region, and here wavelength 7600 angstrom. This region is for Lymon series, this is for Balmer series, and here we get this region is known as infrared. Infrared region, clear? So we get a wavelength while electron transition from higher energy orbit to third energy orbit or higher energy orbit to n1 equal to 3, then we get the spectrum in electromagnetic wave, that is infrared region, clear? So Lymon series lies, or this Paschen series, so this series Paschen series lies in infrared region, clear? Or small infrared region you can write here, infrared region of electromagnetic wave, clear? Of electromagnetic wave spectrum. This region is known as Paschen series. And another one series you can write here, bracket series. Bracket series. In this case, while transition of electron from higher energy orbit n2 corresponding to, it is 5, 6, 7, 8, 9 and so on infinite, to lower energy orbit, and here lower energy n1 equal to corresponding to here 4. So in this case we can write here 1 by lambda equal to r into 1 by n1, n1 is here 4, so 4 square minus 1 by 5, 6, 7, 8, 9 so on you can write here, clear? And if you solve this lambda, then this lambda which will be this angstrom, and this lambda which lies in this region, means lambda we will get greater than 7600 angstrom, clear? In this case the lambda will become which is greater than 7600 angstrom, and this region and bracket series also lies in infrared region, clear? Okay, next one series, or you can say last series of hydrogen spectrum, that is known as P-Fund series. P-Fund series, and here while electron transition from higher energy orbit n2 equal to 6, 7, n1 is here, here 4, so 5, and n2 6, 7, 8, 9 to infinite, higher to lower orbit. Then in this case we can draw the ray diagram Paschen, and this is here n equal to 4, and this series is known as bracket series, and another one series here that is known as P-Fund series. So in this case 1 by lambda equal to r into 1 by n1, n1 is here 5, so 5 square minus 1 by n2 square, n2 you can use 6, 7, 8, 9, you can use any value, but this lambda which will be greater than 7600 angstrom, if you use the value then you will get a wavelength, and this wavelength is lies in the which region? This infrared region, clear? So this is the spectral series of hydrogen atom. So you have to remember which series Lymon series lies in which region of the spectral or electromagnetic wave. So you have to remember this series. This is known as visible region. Here 3600 angstrom, here 7600 angstrom. This region is ultraviolet region, this is visible region, and this region is known as infrared region. And here we get Lymon series. Lymon series lies in ultraviolet region, then Balmer series lies in visible region, and then all the series and rest series. Rest means Lymon, Balmer, Paschen, bracket, P-Fund or funds lies in infrared region. Clear? These are all about spectral line of hydrogen atom. Now let's start. There is another two term, excitation energy and what is excitation potential. That means suppose this is ground state of hydrogen atom, this is fast excited state, this is fast and this is second excited state and third and so on. When electron, it is the amount of energy absorbed by electron, it is the amount of energy absorbed or received by electron from the source, or from the source means here electrical energy, and due to which the electron can jump from ground state to any excited state. That energy is known as excitation energy. Clear? So the amount of energy absorbed by an electron to go from ground state to any other excited state. Excited state is called excitation energy. It's called excitation energy. Suppose electron try to jumps from ground state to fast excited state. This is known as fast excitation energy. Fast excitation energy, or while electron jumps from ground state to fast excited state. But in ground state to fast excited state, so here the excitation energy which is equal to E2 minus E1. E2 means this is fast excited state and energy minus 13.6 electron, 13.4 electron volt minus fast excited state, ground state 13.6 electron volt. Now solve this relation, minus 3.4 electron volt plus 13.6 electron volt, which is equal to 10.2 electron volt, and this 10.2 electron volt is known as fast excitation energy. That means when electron absorb that amount of energy, 10.2 amount of energy, then electron leave the ground state and jump to the fast excited state, or so on. Clear? Or when electron jumps from, we can write second excitation energy. Second excitation energy, and in this case when electron absorbs some amount of energy, at that time it reaches ground state to second excitation energy, or in this case we can write E2 minus E1, and here second excited state energy, that is minus 1.51 electron volt. So minus 1.51 electron volt minus of minus ground state energy, that is 13.6 electron volt, and which comes to be 12.09 electron volt. If electron absorb this amount of energy, then electron jumps from ground state to second excited state, and so on. Clear? So this is all about excitation of energy. So what is the meaning of excitation potential? It is the potential difference, we can write here, it is the potential difference due to which the electron of an atom accelerated to go from ground state to any excited state, and that amount of potential difference is known as excitation potential. Suppose there is two potential difference, here 0 and this potential is V. Now electron move from higher potential to lower potential. Now we have to find here how much potential difference between these 2 points, so that electron can jump from lower energy orbit or ground state to higher excited state. Suppose electron jumps from lower state to higher excited state. So what is the potential difference between these two energy level here? So first excitation potential you can write, that is E2 minus E1, same thing here, minus 3.4 electron volt here potential, and ground state potential, that is minus 13.6 electron volt, and if you solve then you will get that is 10.2 electron volt. That means here if we apply a potential difference between these 2 points, because here minus 13.6 electron volt and here minus 3.4 electron volt, and here delta V means potential difference V2 minus V1, and in this case the potential difference, that is V2 minus V1 or E2 minus E1, which is equal to 10.2 electron volt. If the potential difference between 2 points is here or 2 level is 10.2 electron volt, then electron jumps from ground state to first excited state, and that is known as excitation potential. Or for second state you can write, for second excitation potential, which is equal to 12.09 electron volt. Clear? So these are the concept about excitation energy and excitation potential. And next point here, ionization energy and ionization potential. This is ground level of hydrogen atom. This is first excited state, second excited state, and third. And this is suppose infinite. Here n equal to infinite. This is ground state. Suppose this is ground state. This is first excited state, second excited state, and fourth excited state. So what is the meaning of ionization energy? It is the amount of energy required by an electron to knock out or detach out from the, or to knock out from the atom, and that amount of energy is known as ionization energy. So what is ionization energy? While the atomic gas heated up, then electron or atoms absorb energy. When it absorbs that much amount of energy, so that electrons jumps or electron knock out from the atom, means ground state to n equal to infinite, means last state or last orbit or infinite orbit of hydrogen atom, that amount of energy is known as ionization energy. In here electron knockout means electron knockout from the atom. So in this case n equal to infinite, here energy equal to 0. For ground state, that is minus 13.6 electron volt. So knockout energy, that energy or ionization energy, which is equal to, that is E2 minus E1, and E2 means at infinite minus E1 is here, infinite 0 minus 1.6 electron volt. So finally we get 13.6 electron volt is known as the ionization energy in hydrogen atom. Clear? What is ionization potential? And same thing, there is a potential difference, so that electron accelerate through this potential difference and it knock out from the atom. That potential is known as ionization potential, and here the ionization potential, which is equal to, we can write here potential difference V2 minus V1, that is E2 minus E1 you can write, or V2 minus, that is V1, and V2 is infinite point. If infinite point potential you can write here is 0 minus of minus 1.6 electron volt, then plus 1.6 electron volt. If we accelerate a electron through a potential difference of here 0 potential and 13.6 electron volt, then electron are knocking out from the atom, and that potential is known as ionization potential in case of atom, and which is equal to 13.6 electron volt. Clear? These are all about ionization energy, ionization potential, excitation energy, excitation potential. Clear? Now let's start. What are the limitations on Bohr's atomic model? Actually, Bohr explained the spectral line of hydrogen atom only for hydrogen atom. If there is a atom consists of more than 2 electrons or more than 1 electron, then this formula or then this theory is not valid. So, this theory is only valid for first limitation. It is only valid for hydrogen atom or hydrogen like atom, H like atom, H like atom. It could not explain the complex atom which consists more than 1 electron. So hydrogen like atom means suppose there is a atom, helium atom, suppose E, and its proton number, that is 2, atomic number 2, and if we release 1 electron from the helium atom, then we can add here positive charge and it only possesses 1 electron like this. Clear? And here this atom 1 electron, then it can valid for Bohr's atomic model. Suppose you can take lithium 3, atomic number 3. So if we release 2 electron, then it get a positive charge and only 1 electron is here. So this type of atom can possible for valid the spectral line in hydrogen atom case or in Bohr's atomic model. So this is the first limitation of Bohr's atomic model. So this is about the first limitation. Second limitation, it does not give any idea about arrangement and distribution of an electron in hydrogen atom. Suppose there is a hydrogen atom plus and this is nucleus and this is the first orbit, then how many numbers of electron are represented in arrangement of the electron in first orbit? It could not explain Bohr's atomic model. And second, next thing, it could not explain the wave nature of spectral line, because according to de Broglie wavelength lambda equal to h by p or lambda equal to p equal to mv. If particle possess velocity, then it possess wave nature. That means every moving particle consists or every moving particle which associated with a wave, because here electron is moving in a circular path with some velocity. That means electron is here moving particle, so it must possess or it must associated with wave, which could not explain which could not explain Bohr's atomic model. So these are another limitation, and it cannot explain the nature of spectral line, wave nature of spectral line. Next, it is violate to Heisenberg uncertainty. Heisenberg, most important scientist name. Uncertainty principle is famous principle. According to this principle, we cannot measure position and momentum at a particular time of the particle. Suppose there is an electron which is situated at a distance r and moving with some velocity v. If it moving with some velocity v, then it possesses momentum p equal to mv. At a particular time, it gives the indication of particular time which give us the position and momentum of the particle, which is not possible according to Heisenberg uncertainty principle. So Bohr's atomic model, which is violate to Heisenberg uncertainty principle, this is another one limitation of Bohr's atomic model. Then it cannot explain the splitting of spectral line while we introduce electric field and magnetic field. If we place it cannot splitting. If we use electric field and magnetic field, we cannot splitting the spectral line. And finally, which was, that is for electric field, the spectral line is known as Stark effect. For magnetic field, this is known as Zeeman effect. And this Stark effect and Zeeman effect you will study here. You will study your next level or higher study. Clear? So these are all about hydrogen spectrum, different type of series or transmission of series, and these are the limitation of Bohr's atomic model. Clear? So you have to remember this formula, this postulate of Bohr's atomic model, Rutherford atomic model. This is most important long question for your council examination. Clear? Thank you all.